next speaker is Professor Ningjun Jiang from Southeast University. Professor Jiang's research areas include biomediated geotechnics and soil remediation. He received a Ferdinand Award from Canadian Geotechnical Society in 2019. Dr. Jiang is editorial board member of Soils and Foundations and Environmental Geotechnics. Today, his topic is engineering performance of bio-stimulated MICP treated on calcareous sand. Okay.
Good afternoon, everyone. I'm Ningjun Jiang from Southeast University in China. Firstly, I would like to thank ISEG Organization Committee for their invitation to deliver a presentation today. So today, the topic I would like to talk about is engineering performance of bio-cemented calcareous sand treated through biostimulation. So as you may know, calcareous sand is a very special earth material. It comes from the carbonate skeleton of marine organisms and is widely distributed in tropical regions around the world. So calcareous sand particles are normally highly angular and their surfaces are quite rough. So calcareous sand itself is typically high in water ratio, crushability, and compressibility, and its strength is relatively low. So due to these reasons, so when used as foundation material, calcareous sand has to be, reinforced to meet the design construction and requirements. So then, microbial-induced calcium precipitation, or MICP, is a promising soil improvement technique and has gained a lot of attention in the recent years. So the idea of MICP is that nature urealytic bacteria could produce urease enzyme. So this enzyme then could hydrolyze the urea to produce carbonate and ammonia. And at the same time, the environment pH is also elevated. So then with the slightly alkaline condition, then if there are calcium ions present, then the calcium ions can react with carbonate to generate calcium carbonate precipitation or calcite precipitation. This precipitation, when present between loose sand particles, can serve as interparticle bonding and increase the overall mechanical strength of the sand. So currently, the research in MICP is quite active worldwide at all scales, ranging from micro scales to macro scales to the field scales. And here on the right-hand figure, I listed a few featured researches at different scales. And due to time limit, I will not talk about them in details. Okay, so then the approach to achieve MICP, right? There's two. One is biostimulation and the other is bio-augmentation. So bio-augmentation is a more typical way, meaning that, a standard or, a known bacteria species is cultivated in the lab, and then the bacterial solution is injected into the ground to trigger MICP reactions. So, but the disadvantage of the bio-augmentation method is that the compatibility of the injected bacterial solution with the, nature environment is questionable, and sometimes, the injected standard bacteria may not survive so long time. Then, in addition to bio-augmentation, then biostimulation is an alternative way to achieve MICP. And there's also two approaches to achieve biostimulation. One is ex situ, the other is in situ. Ex situ means that the urealytic bacteria is extracted, isolated, and purified from the, sampled nature soil. Then the bacteria are enriched in the lab and then re-injected into the ground. So through this method, of course, the compatibility of the injected native bacteria and the nature environment will be much better compared with that in the case of bio-augmentation. However, the processes involved in ex situ biostimulation are quite complicated, right? So then it comes to the next approach, the in situ biostimulation. In this method, instead of injecting bacteria, only carefully designed enrichment medium will be injected, and the medium can stimulate the growth of native urolitic bacteria in the soil, in the natural soil, and then it can trigger MICP. So compared with the rest two approaches, it's much simpler, and and also the whole process is relatively easy, and there's no problem regarding the compatibility of bacteria and the natural environment. So in this study, we will focus on the in situ biostimulation method. Okay, so actually this is a very big project. So the biostimulated MICP for calcareous sand stabilization. In this big project, we look at three aspects: optimization, performance, and application. For the optimization, then we focus on the phylogenetic characteristics, various kinetics, and chemical reactions by doing solution batch test, column culture test, and genetic sequencing. For the performance aspect, we've characterized the bio-cementation level, shell strength, and compressibility by doing direct shell test, traxel shell test, and odometer test. And finally, for the application aspect, we focus on ground improvement, coastal erosion control, heavy metal immobilization by doing 2D tank test and hydraulic film test. So in today's presentation, I will mainly focus on the first two aspects, optimization and performance. Okay, so firstly, let's look at the optimization, right? So here, firstly, we performed the solution batch test. So the purpose of solution batch test is to find out what are the most significant factors that control the enrichment of indigenous urolitic bacteria, or stage 1, right? So actually, as mentioned, right, the biostimulation has two stages. Stage 1 is to stimulate the growth of bacteria, and stage 2 is to form bio-augmentation, right? So here, we only look at stage 1, what are the most significant contributing factors. So for the test, right, we mixed 1 gram of beach sand with the enrichment solution. Here we have 3 types of enrichment solution: YE is extract, ME multi-extract, and NB nutrient brush-based, urolitic enrichment solution. Because in this solution we also have urea inside. Okay, so when they are mixed, then they are subject to shake incubation for different periods, and then the samples are subject to pH, electrical activity, and ammonia concentration measurement. Also, we performed the viable cell number counting. Okay, through this test, then we performed the analysis of variance to get the p-values. And a very small p-value means that a certain variable is very significant, right? So from this analysis, we can clearly see that the incubation time, right, or the stimulation or enrichment time, then the concentration of urea in the enrichment solution, as well as the medium type, are the most significant factors that may affect the enrichment stage, right? So then, in order to further determine what are the optimized, like urea concentration and stimulation time, then we did the soil column test. So it's quite similar to the solution batch test. Only different is that we directly inject the enrichment solution into the soil column, and after a certain period, then we take soil samples and measure the urea concentration and ammonia concentration. So here are the results. So clearly, if we see the black lines and dots, we can see that with the increase in urea concentration, right, from 50 mole to 100 to 170 mole, then the ability of the enriched bacteria to consume urea concentration also becomes higher, right? It means that the generated urealytic activity is higher, right? So from this test, we can see that actually 170 mole or 100 gram per liter urea is sufficient to effectively induce, biostimulation, right? So that's already a lot, enough urealytic bacteria enriched at this concentration. Then also we find that after 48 hours, regardless of the medium, whether it is YE or NB, we can see right after 48 hours, all given urea has been consumed, right? It means that after 40 hours, it's already done, right? We already have sufficient amount of urealytic activity from the stimulated bacteria, right? So that's why we choose 170 more urea and 48 hours our following tests. Okay, so then it comes to the performance aspect. Right? So in this part, okay, so firstly, I would like to introduce the material and testing method. So the soil sample, again, is sourced from, Waikiki Beach in Hawaii, because this is the study I performed in Hawaii. And then we perform the enrichment medium, which contain either ISEG or nutrient brass and urea. Right, so this is a composite material. And then we have cementation solution, which aims to generate bio-cementation, right? Within the cementation solution, there are calcium, urea, and trace nutrition additive. Okay, so then for the first 48 hours, right, the enrichment medium was percolated on the surface, through the surface of the soil sample to stimulate the growth of the native bacteria, as mentioned, right? 48 hours is the optimized time we found. And the concentration of urea within enrichment medium is 170. Okay, then after 48 hours, then we, percolate the cementation solution once a day for 5 to 10 days. So the aim of this percolation is to generate bio-cementation at different levels, right? The longer period of percolation we perform, then the higher cementation level we expect. Okay, so then after that, right, we got the bio-cemented sand samples. Then we performed the cementation content measurement and direct shell test, track shell test, and automate test. So here is the overview of the experimental program, as you can see, right? So we have 2 enrichment medium. Then the soil samples are prepared at 2 different relative densities. One is low, 16.2%. The other is high relative density, 54.6. Then for bio-cementation treatment, right, we selected 2, cementation solution concentration. One is 0.3 mole, the other is 0.5 mole, and 2 percolation periods, 5 days and 10 days. So this will give us different cementation levels. Okay, so firstly, let's see the cementation content results. So here there's several columns, right, divided into 4, boxes. In each box, right, from the left to right, we can see that the cementation content increases. Actually, from the left to the right, we can see that either the cementation solution concentration increases or the, treatment period increases, right? So here, then we can conclude that higher cementation solution concentration as well as longer treatment period could lead to higher cementation content. And this is true for all 4 cases with different enrichment media and relative density. And meanwhile, we find that if we compare these 4 boxes, actually the initial relative density and the medium type do not significantly influence the cementation content level. Then we also actually performed the microscopic observation using optical microscopes. So in picture A, so this is uncemented sand, as we can see, the loose sand without any cementation or bonding between particles. Then for figure B, then this is a low cementation level case. We can see a little bit, interparticle bondings, but not that obvious. However, for the heavily cemented case, which we have 6.33% cementation, then we can see quite obvious, wide interparticle bonding or cementation between the sand particles. In addition, we also see, many calcareous sand particles are coated by this kind of white cementation, right? So these two graphs can prove that the biocementation are effectively generated. Okay, so next, let's see the quick shell test results. Firstly, is the stress ratio displacement relationship. Obviously, so here I just pick up one representative case, right? So with the increase in the normal stress, then the peak shell stress ratio, the peak stress ratio drops, right? And also the strength corresponding to the peak also increases. And if we look at the vertical displacement, horizontal displacement relationship, so at low normal stress, 50 kPa, then the soil is quite dilated. However, if the normal stress is like 600 kPa, right, like when it is elevated, then the dilation of the soil is kind of suppressed, right? It becomes more contractive. Okay, so that's a general, shell behavior during direction test for the biocemented case. Then we systematically summarize the peak stress ratio results and correlate it with the cementation content. So the left-hand graph is low initial density case, and the right-hand graph is high relative density case. So here we can see that firstly, the peak stress ratio increases with cementation case. So this is true for all samples, right? So it means that cementation can help improve the shell strength, right? Peak shell strength, peak shell stress of, the calcareous sand, right? However, this increase, right, is diminished with higher confinement, right? So like for 50, we can see the slope is quite large, right? So this increase is quite significant. However, at 600 kPa normal stress, then with increasing concentration as cementation content, then the improve in peak stress ratio is not that significant, right? So this diminishing effect is obvious. And finally, it seems the initial density does not have a quite obvious effect, impact on the peak stress ratio. Then, based on the direct shell test, we also obtain the cohesion and friction angle based on the Moore-Coulomb theory. And here, this graph shows the cohesion versus cementation content. So obviously, with the increase in cementation content, cohesion is increased, right, due to the formed interparticle bonding, right? So cohesion, improvement in cohesion is quite obvious. And if it is compared with previous studies, we can see that at the same cementation content, right, the cohesion in our study, measured in our study, is higher in two previously reported studies, meaning that potentially this bio-stimulation method is more effective because these two previous studies were all about bio-augmentation, not bio-stimulation. And secondly, here I didn't put the friction angle data, but actually we find that the cementation content does not significantly influence friction angle, no significant improvement or reduction, right? So only cohesion is apparently affected. Okay, so next is the CU traxel shell test, right? So on the left-hand graph, that's the picture taken at the end of two CU traxel shell tests. One is under 400 kPa confined pressure, the other is under 50 kPa, right? On the 400 kPa, right, the high level of confining pressure, we can see clear shell band, right? However, for 50 kPa, it's like barraging. Then on the right-hand side graph, so this is the effective stress pass graph. Okay, so on this graph, the dotted lines represent the uncemented, right, the clean sand, and the solid lines represent bio-cemented sand. So here we didn't vary other parameters like cementation, solution concentration, treating time, sort of things. We only pick up one fixed cementation level. Okay, so from the effective stress pass graph, firstly, we can see that for both uncemented and bio-cemented sands, they exhibit strength hardening behavior, right? Because they CU test. And secondly, after bio-cementation, the sand exhibits the shear behavior like dense sand, right? So compared with the uncemented case, right? The effective stress pass shifts to the right, right? And this is especially true at lower effective mean stress, right? So for clean sand, it's more like loose sand, right? Like loose sand. However, after bio-cementation, it becomes more like dense sand. Okay, then finally, if we look at the critical state line part, right? In some samples, maybe the critical state is not fully reached, but in general, we can see that after bio-cementation treatment, then the slope of the critical state line increases. So, and it is higher location of the critical state lines. The bio-cemented samples are higher than that of untreated samples. Then from the CU Traxel shell test, we also use more Coulomb theory to get the peak and the residue cohesion and friction angle, right? So left-hand side graph shows the peak state, and the right-hand side picture and shows the residue state. So from this one, we can see that. So the red one represents the high cementation level case. The solid black one represents the low cementation level case, and the dotted one shows uncemented case. So obviously, with bio-cementation treatment, right, the cohesion, the effective peak cohesion increases from 0 for uncemented case to 41.6 for the high cementation level case. And however, if we look at the effective friction angle, right, actually it does not change too much. So it means that the peak friction angle is sort of independent of cementation content. Then for the residue state, so firstly, we find that the cohesion is fully mobilized, right? So there's no cohesion at this state. So it means that all effective bonding has been broken as a residual state. And secondly, if we look at the effective residue friction angle, right? Again, it does not change too much with the cementation content. Okay, so finally, it's the ultimate test or one-dimensional compression test. So from this test, we can obtain the compression curve. So here, because the soil samples have slightly different initial water ratio, so here we perform the normalization. So the vertical axis will be the normalized water ratio, and the horizontal axis, the vertical stress. So we perform it, and from the black one to the purple one, then the cementation level increases, right? So from the graph, you can see that with the increase in the cementation content, then the compression curve generally move upward, right? So the transition becomes more steep, right? More abrupt with the increase in cementation content. And accordingly, if we look at CC, the compression index, and CS, the swelling index for this part, right? So with the increase in cementation content, CC increases and the CS reduces, right? And finally, if we look at the rebound state, interestingly, right, even if the cementation content different, but the slope for this part, or we can say CR, the rebounding index is very similar among these cases. It means that the rebound state actually is kind of independent of cementation content. And this can further prove that at this stage, the soil has been fully, that the interparticle cementation has been fully broken. And during the automated test, we also evaluated the relative breakage, right? So firstly, I would like to briefly introduce the concept of relative breakage, right? As you can see on the left-hand graph, so this is the typical particle size distribution curve. So in this graph, the black one represents original PS, the particle size distribution curve of clean sand. And the blue one represents the particle size distribution curve of bio-cemented sand after loading. I mean, at the end of the compression test. So interestingly, we can say that at the final particle part, right, for the parts, smaller than 0.6, the particle size distribution curve moves to the top of that of clean sand. So it means that actually we have more fine particles generated during the compression process. So then the relative breakage is defined as a ratio of the area of OFGO and the area of ABOG. As you can imagine, right, if we have more fine particles, right, generated during compression, then this ratio, the area of OFG will become larger. So the relative breakage will become larger as well. Okay, so then we plot the relative breakage BR with cementation content, right, the data from different cases. Okay, so firstly, actually, we also did a control test. So for the clean sand, so after compression on the clean sand, actually, we didn't see any noticeable change in particle size during curve. It means that the calcareous sand particle itself does not break, right? So we can see that the generated fine particles during the compression of bio-cemented sand are from the broken interparticle bonding. However, with increasing cementation content, the BR value reduces significantly. It means that if we have a lot of cementation content, then it is unlikely that, or in other words, the breakage of cementation bonding will be less severe, right? Less severe. And also, we find that with the increase in the initial relative density of the soil sample, then the BR values are also lower. That's because, for initially low relative density samples, then the interparticle bonding or cementation are more likely to locate it in, better places to form better bonding, right? So the relative breakage will be smaller. Okay, so these are the mechanical performances we obtained from series test, and here are the main conclusions. Firstly, so we find that 170 more urea and 48 hours stimulation time are sufficient to stimulate enough indigenous ureatic bacteria. And secondly, we find the high bio-cementation level can be achieved by applying higher cementation solution concentration and for longer treatment period. And thirdly, in the direct shear test, shear stress ratio, so here I mean peak shear stress ratio increases with cementation level, but is suppressed with elevated confinement. Then in the CU traxel shear test, effective cohesion increased substantially with cementation content. Friction angle, however, is independent of it. Then in the automated test, the compressibility of calcareous sand and the bonding breakage during compression are dramatically reduced after subject to bio-cementation treatment. So through these observations, we can finally conclude that bio-stimulated MICP could effectively stabilize calcareous sand without introducing bacteria cultivated in the lab. Thank you for listening. And if you have any questions, please feel free to send email to jiangn@seu.edu.cn. Thank you.